Okay, so in an attempt to go further than in our earlier discussion, at this point, we looked at this three-stage process where you have a claim in mind about some parameter of the population, like in this example, that the proportion of the population is greater than 20%, and that from that claim, you go through this three-step process. Step one, formalize your claim using notation. Step two, give symbolic form for the notation that would be true if your claim was wrong or false. And then step three, use those formal notations to identify a null and an alternative hypothesis, where the null hypothesis is always a claim of equality about this parameter, and the alternative hypothesis will be either less than, greater than, or not equal to, depending on which one made sense from the first two steps that you did earlier. So let's say we can see another example to implement this. And they do drone deliveries here in their example. So we're going to instead try to focus on the example we were just looking at and skip over the first couple slides where they do that three-step process. So by the end of their step three, they have a null and alternative hypothesis. And then they want to discuss this idea of significance level. And we didn't get to this in our earlier discussion. So here's where we're going to try to go a little further than we did before. So let's first define this. So first of all, I point out from what we have from before, I'm going to say we have a claim. And that is that P is greater than 20%, some proportion claim. And that led us to being able to produce a null hypothesis that the proportion is actually not greater than 20%, but is equal to 20%. And an alternative hypothesis, which is actually our claim in this case, that the proportion is actually greater than 20%. Oops. All right. So somehow our three-step process allows us to create this null and alternative hypothesis related to our claim. So what is this concept of significance level? Now, we've looked at significance level alpha before. For example, if we had a confidence interval that was 95%, then alpha was the other 5%. You're 95% sure that your parameter is in this range of values, and you're 5%, possible that you're wrong. So the significance level usually is the amount of probability that your claim is wrong, or that what you're saying about the population is wrong. So here it states the significance level alpha, same symbol, for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitute significant evidence against the null hypothesis. What the heck does that mean? By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it's true. So the way they try to sum this up, alpha is the probability that you don't believe the null hypothesis when it really is true. So let's give an example to go along with the example we've been working with so far. Say we let alpha be equal to the most common value, 5%. So if I have a significance level of 5%, then what that means is that the probability is 5% based on my sample that I took, that I will reject the null. What was the null? The null was that the proportion of blue wearers is 20%, when it's actually true. So let's say I take a sample and I see in my sample that 22% of the people in my sample were wearing some blue. So the question then is, does that 22% in my sample support my claim that the proportion is greater than 20%? Or does it not support my claim that it's greater than 20%, meaning that it could be 20% or less? And so if it were equal to 20%, which is the null hypothesis, my claim is wrong. So if I reject that it's 20%, that means I'm supporting my claim that it's more than 20%. So rejecting the H sub 0 means supporting the alternative hypothesis, which in this case is our claim. So that will depend on sample size, for example. So if I get 22% in my student sample and I took 100 people, then what we're going to say is that I want to make sure that I'm going to say that that supports my claim. The 22% I got supports my claim that the real proportion is more than 20%. I'm only going to make that assertion if the chance that I'm claiming it's more than 20% is supported by my sample, if my sample would have only come out that high above 20% less than 5% of the time. And so you may recall StatCrunch will give you this thing called a p-value. So if I give my information over to StatCrunch and it gives me a p-value of 2%, and I told it I gave 100 people the sample question, I looked at what they were wearing, 22% of them were blue, 22 out of 100 were blue. If I give the StatCrunch my null hypothesis and my alternative hypothesis, and it says the p-value is 2%. Well, then what I do is I say, well, that p-value means that the chance that I would get 22% when the actual population proportion was only 20%, the chance I would get 22% is only 2% likely. The p-value is the likelihood based on assuming the null hypothesis that your sample would come out the way it did. And if that p-value is very low, that suggests that the null hypothesis is wrong and you should reject it. And that's evidence in support of your alternative hypothesis. If there's only a 2% chance that I could sample 100 people and get 22% wearing blue, when in actuality only 20% wear blue for the whole population. Well, if the chance of getting 22% is low, is only 2%, well, that's evidence in support of rejecting that it's only 20% and supporting that it's more than 20% like I claimed, because my sample was enough more than 20% to make me believe my claim is true. That's tough. We are almost out of time. That's the idea. That's my introduction to the idea of a significance level. And here's the conclusion that you will use to draw your evidence statement. If, this is the rule of thumb, if the p-value is less than alpha, in this case, if my p-value is 2%, and my alpha value of significance is 5%, well, then that's low enough of a chance that my sample would come out this significantly high a proportion. That's low enough of a probability that I don't think it was by chance. I think that it is really more than 20%. I reject the null hypothesis that it's 20%, and I say this is evidence in support of my claim that it's more than 20%. If the p-value is less than the alpha value, then you reject the null hypothesis and you support the alternative hypothesis. Ultimately, we say, here's the phrase that to start to remember, if the p is low, the null must go. Meaning you reject the null. If the p is low, meaning below alpha, then the null must go, meaning you reject the null hypothesis. If the p is low, the null must go. Okay, so our class had to end at this point, but I want to push the introduction of these topics a little bit further. So I'm going to continue on without a live audience. So here's where we left off. We were looking at the idea of a significance level for a hypothesis test. And the rule of thumb, or the phrase to keep in mind, is that if the p is low, the null must go. Meaning that if the p value is less than the significance level alpha, then you reject the null hypothesis, and instead you have evidence in support of the alternate hypothesis. So we need to see this in action and try to look at what they mean by this. And also they're going to look at two different ways to determine whether you should reject the null hypothesis. One is by looking directly at a p-value, and that's what we'll use most frequently when allowed to do so, because StatCrunch just provides that to you. But the other is to come up with what they call a critical value for your distribution score that you can then compare to the test statistic, which we've calculated already, sort of the distribution value of your sample, and see if your sample's test statistic has a score that demonstrates that the value is significantly high enough so that the p-value would be low and you would reject the null. Anyway, a little hard to follow just from describing. So let me move forward with the slides a little bit. And again, we are skipping through their example about drone usage in order to just look at the definitions such as this one that they're highlighting. So they point out the significance level is the same alpha introduced in earlier sections. And so in the example that I was just using, I said the default is often this 5%, but alpha could be 1% or 10%, but 5% is most common. But nonetheless, we will just use whatever significance level that the problem dictates. And if folks get to the point when they're writing up their projects and doing their own data analysis and testing their own hypothesis tests, claims, then you can choose your own significance level. All right, but moving forward, just seeing that it is a flexible thing. It's not always 5%, but could be. So then what you do, one of the ways you can approach analyzing the data is to identify the test statistic that is relative to the test and determine its sampling distribution. So as I've been discussing, as we also did with confidence intervals, you want to know which distribution you're using. Are you doing a proportion sample? Are you looking at the mean value? Are you looking at the standard deviation? And if you're looking at the mean, you might have a student t distribution, or if you're looking at the mean and you know the standard deviation of the population, you'll just use a normal distribution. If you're looking for standard deviation, you'll use the chi-square distribution, which again is that funny symbol right here. So you have to identify that. So we'll need to do that, and you'll see as we do problems that that's a key thing to choose the correct distribution for your hypothesis test. Then they talk about identifying the test statistic, and we've done that in problems already. And again, when we do that, we don't really choose to use any of these formulas if we can avoid it. Instead, we use StatCrunch. So not worrying about the formulas on this slide, we do need to recognize that we might be asked to identify the test statistic of our sample. And again, the test statistic is the distribution score, maybe a t-score, maybe a z-score, that your sample gets on the distribution, the distribution score of your sample. So skipping by their example, so let's look at this next goal related to the significance level. finding the value of the test statistic, then find either the p-value or the critical value. So let's go back to our situation. We have a claim. And I was still going to use that the proportion of students randomly chosen at DVC, or the students at DVC that wear an article of blue clothing is greater than 20%. And this, again, led us to a null hypothesis that would cause our claim to be wrong, that our proportion isn't greater than 20%, but that it's actually just equal to 20%. And an alternate hypothesis that is what we're claiming, that the proportion is greater than 20%. And I was suggesting that we're going to let our significance level alpha be 0.05 or 5%, which is most common. All right, so what do they mean, finding the value of the test statistic? So you have this claim, you have this hypothesis that you're going to test. You've used it to identify the null hypothesis and the alternate hypothesis, and you have a significance level with which you're going to try to run your test. So the idea behind the p-value, the critical value, and the test statistic is that you will have some distribution, and you're choosing your sample randomly, and there's some distribution. And so what you're going to do is you're going to make a distribution based on the assumption that the null hypothesis is true. So we're going to say, let's assume that the proportion of blue clothing wearers is 20%. That would mean that I'm assuming that my claim is false. I think it's greater than 20%, but let's say I'm wrong. Let's say it's equal to 20%. That's the null hypothesis. So if we assume that, then we can create a distribution, and this would be a normal distribution because this is about proportions, and we use a normal z-score distribution for proportions. And my mean population, the population proportion of students who wear an article of blue clothing is 20%. That's my assumption. So then, with that in place, we then look at the results of my sample. I take a sample of 100 students, and I get some result. So say that the proportion of my sample turned out to be 0. I think I used 22 before, but I'm going to say 25%, just to use different numbers. So say I take a sample of 100 students, and so my sample size n is 100. And it turns out from my sample, 25 of them have some article of clothing that has blue. And so my sample proportion is 25%. So again, here is the logic backing all of this up. From a sample of 25%, is that convincing enough for me to say, well, the sample was enough above 25% that I'm going to reject the assumption that the actual population proportion is 20%, because I think if it really was 20% for the whole population, well, then the likelihood that my 100 sample size would have 25% is too low. Well, that depends on that likelihood. If it's very easy when you take a sample of 100 to happen to get 25% when the actual population has a 20% proportion, well, then that's not very convincing evidence. And as we discussed in earlier examples, what if it was 21%? What if it was 20.3%? If you had barely over 20, then you can imagine that that's not very convincing, that that's not good evidence. That's not sufficient evidence to assume that it has to be greater than 20% for the entire population. But the higher your sample goes, the stronger the evidence seems to be that the actual population proportion really needs to be more than 20% because that's just too hard to have happened. And so this is the concept behind if the probability is low, the null must go. If the probability that I could get my sample this much above 20%, if the probability of having that happen when the actual population proportion is 20%, if that makes this result so unlikely that I then say, well, instead, I really don't believe it is 20%. I think this is sufficient evidence that it must be more than 20%. So how unlikely would my sample need to be? How low of a p-value do I need to have to reject the idea that it's 20% and show support that it's more than 20%? The p-value needs to be below my significance level of 5%. So I would want to enter this information into StatCrunch, and it would give me a p-value, and it would give me this thing, the test statistic. So this result of 25% with 100 people, well, if the population proportion really is 20%, then getting a sample of 25% would produce a z-score somewhere. So if I have over here a p-hat value of 25%, then that's going to give me some sort of a z-score, which I don't know off the top of my head. You have to calculate that. And that z-score will have a portion of area up here that would show me whether that is significantly high or not. The area in this region is the p-value. Again, the p-value is the likelihood that I would get a sample as high as a proportion of 25% with 100 people sampled, or higher just by random chance. What is the likelihood if the proportion really was 20? That's my assumption. Well, what's the likelihood I could get a sample like that? Well, that will be how much area is at that level or higher in my distribution. That's the p-value. The z-score for that p-value is the test statistic. So the idea is when you do your sample and you have a claim and you have a significance level, then you find the value of your test statistic, then find either the p-value or the critical value. So let me go ahead and try to define the critical value. Let's see if they do that on the next slide, because it is in bold here. Well, they have the test statistic, then they go back to their sample, then we have critical region. That's where we'll define the critical value stuff. All right, so this is the idea of what's going on and my attempt to make a little picture about it. So let's look at how they tell us what this test statistic and p-value are defined to be with this example that I've given in mind. So the test statistic, as I just was showing here, is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, might be proportion, might be a mean, might be standard deviation, to a score, such as a z, t, or chi-squared score. So that's why up here I put that you would get this z-score for a test statistic, because for proportion samples, you get z-scores, with the assumption the null hypothesis is true. So if the null hypothesis is true, if the proportion really is what the null hypothesis states that it is, well, then how rare would that sample be? What kind of a z-score would you get? Remember, the higher the z-score, the more rare or more significantly hard to get those kind of scores are. And so bigger z-scores, higher z-scores mean more rare occurrences. And so if the sample we get has a very rare, very high z-score, assuming the population is 20% proportion, well, that's evidence that actually maybe it's not 20%. And the reason maybe it came out so high is that the proportion is really higher. That's the logic. So that's the definition is this test statistic is the z-score or t-score or chi-squared score, the distribution score that your sample would get. And that helps you determine whether that's significantly high enough of a sample to reject the null hypothesis, to reject your assumption. The assumption is that the null hypothesis is true. And if the test statistic is very extreme, we reject that. If the test stat is extreme or significant, we reject the null hypothesis. So that's the logical idea behind what we're trying to accomplish here. All right, so they do their example where they do it. We'll just do that in StatCrunch. But let's see what they do with that. All right, so just they're now going to define this thing, the critical region, because the critical region is how you identify whether your test statistic is extreme enough or not to reject the null without using a p-value. The critical region or the rejection region, that's just that region I drew up here where I showed the p-value. So let me label that here. The p-value is the area here. And this region that I've highlighted here is called the critical region. So the critical region sort of shows you, actually, that's not exactly right. I identified the p-value. So let me retract that because I'm kind of doubling up here a little bit. Let me adjust this a little bit. So you have this good enough. So you have this area that's the p-value. That's shown by where your test statistic is. So what I'm going to do is I'm going to draw another thing here. And so if we are saying that our alpha value is 5%, then what that means is we're looking to see if our test statistic produces a p-value less than 5%. And so the critical value would be the z-score you would need, in this case a z-score, that marks the 5% point on the distribution. So if I was saying that my significance level is 5%, then I could say that means that if I get a z-score on the distribution high enough so that to the right of the z-score is less than 5%, then I reject the null. And the critical value is the z-score required to make that happen. So I'm going to label this, it has a critical value here. Now, in my little sloppy picture here, we can see a z-score for the test statistic that is to the right of the 5% level. Therefore, it's larger than the critical value. And therefore, because the test statistic was larger than the critical value, then the probability of getting that rare a sample is less than 5%. And that's why we reject the null. So the critical value is the score that you would need for the test statistic to surpass in order to reject the null. And it's based entirely on the significance level. The critical value, so this leads to a critical value. So how extreme, how sure, how low you want the probability of getting your results just by random chance, how low that needs to be satisfied, that's determined by the significance level. And again, that might vary, but the most common is 5%. Once you know what significance level you're shooting for, you can produce the z-score or the t-score or the chi-squared score of that critical value. And that tells you, all right, you need to be at least here in the distribution to have the rarity of your sample occur less than 5% of the time. And then whatever that z-score is, if you get a test statistic for your sample bigger than that, then yes, that is significantly high based on your significance level, and you reject the null. And equivalent to that is you can just look at the p-value you get for your test statistic and see if that's less than 5%, and then you reject the null. So that's the two ideas. That's why it says either the p-value or the critical value is how you would do this. All right, so let's see if we can get to a specific here a little bit. So it says, I think I'll do a specific by doing my stat lab problem for you so we can try to see what's going on here. So let's do that right now. Well, let me just mention that the other possibility, and we've got tails here to discuss this too, the other possibility is the p-value method. And as I was just discussing, in a hypothesis test, the p-value is the probability of getting a value of the test statistic at least as extreme as the one you obtained from your sample, assuming the null hypothesis is true. It's the probability that you could get that rare of a sample if it was true. And if the probability is very low, the null must go. So let's illustrate this. I'm going to try to illustrate this with an example in StatCrunch. So let's go to a StatCrunch problem. So I grabbed number 14 on the current sort of homework set. And it's asking us for these same kind of things. So it says there's a test statistic, z equals -1.94. That's obtained when testing a claim that some proportion of something is less than 47%. So in this case, let's continue. In this case, they're not even trying to give us the context of a real world problem. They're just trying to understand if we can demonstrate these underlying interactions between test statistics and p-values and things like that. So it says the test statistic of the z value, the test statistic is a z value of -1.94. And so we're supposed to use a significance level of 0.10 and find the critical value, and then determine based on the test statistic by comparing it to the critical value whether we should reject the null. All right, so let me see if I can get a picture here that will help us in this problem. So we have there's a claim that p is less than 0.47. And remember, from that claim, we can identify the null and alternative hypotheses. And we'll need to do that in this problem because part B, we're supposed to determine if we should reject the null. So if the claim is that proportion is less than 47%, then the null hypothesis would be that the proportion is equal to 0.47, because the null hypothesis always includes equality. And then the alternative hypothesis would be that the proportion is less than 0.47. And so if we try to visualize that, that means we have a distribution in which we are assuming the null hypothesis, which is that p is equal to 0.47. And then we're going to try to determine if our sample results are significantly, in this case, low enough, because our claim is below that it's 0.47, that they're significantly low enough for me to conclude that I should reject the assumption that it's equal to 0.47. And they tell us we have this z-score here for the test statistic of negative 1.94. So that means I'm somewhere over here. I have negative 1.94 is my test statistic. So from that value, this part to the left of it is our p-value. This is the p-value. This is the region of area that would show the likelihood of getting that test score or lower just by random chance, assuming that the population proportion really is 47%. And we don't even know what the test statistic, we don't even know how many people they sampled or what the proportion of the sample was. We just know that it produced a test statistic, a z-score for that sample on the distribution curve of negative 1.94. So what we want to do first is find a significance level alpha 10% critical value. So they tell us that alpha is equal to 10%. And the critical value will be the place on our distribution curve. And I don't know whether it will be above or below this point here. But imagine that, let's just say we had this is same distribution. Somewhere in this distribution is a place where the area or the likelihood of getting that high a score is 10%. And so since we have a significance level of 10%, the idea is the test statistic low enough to the left enough to pass that 10% level? If this test statistic of negative 1.94 is over here, well, then that means that you would have 10% or less. And instead, if it was over here, you would not have 10% or less. So we want to compare that value to the critical value. And this region over here is called the critical region. The region of the critical value. Now, in this case, we know the critical region has an area of 10% because that's our significance level. So that's the idea of what we're doing here. To do this problem is pretty straightforward. So first of all, the first thing they ask for is to find a critical value. So that means I need to find the z-score where to the left the area is 10%. I need to find what is this z-score here? What is this z-score at the 10% level? So I'm going to leave all these drawings up here for a second because this is so easy to do in StatCrunch. So to do that, I would open up StatCrunch. And I would go to Stat, Calculator, and this is a z distribution, a normal distribution, because it's for a proportion. So I would go to normal. And so here we're getting a picture that matches what I want here, but I want to find the location where this critical region is 10%, because that's how far I need to get to satisfy a 10% significance level. So what I'm going to do is I'm going to just change this from 50% to 10% and compute. And then it shows me that at negative 1.28, at that z-score level, then the area to the left of that is at 10%. So that means that the value I want in here, in my little circle here, is negative 1.28 something, something, something. That also then shows me that the actual test statistic of negative 1.94 is to the left of that. So that means if I put the two on the same thing, then the critical value ended up being to the right of our test statistic. So it's over here somewhere. So the critical value was here, and our test statistic was to the left of that. But first of all, let me enter that in. So I would put in a critical value of negative 1.28, says to 2 decimals, okay. So it's happy with that. So now, based on this fact, then the question is, do we choose correct conclusion below? Do we fail to reject the null, or do we reject the null? And what do we conclude based on that? So let me just clear all my stuff here. So we got a critical value of negative 1.28. And we compare that to the test statistic of negative 1.94. Because on our curve, we are looking to see, so we move the curve over here. So at this point, you have 10%. And at negative 1.94, you would be over here somewhere. And since that's to the right of where you have 10%, you clearly have less than 10%. And therefore, the p-value, which would be left of the actual test statistic, p-value, is low enough, or the test statistic was extreme enough to say that this was very unlikely. There was less than a 10% chance that you would get this test statistic based on your sample if we assume the null hypothesis, which is that the actual proportion is 47%. If that were true, then this sample would be very unlikely. So because that's very unlikely, we say that's evidence to reject the assumption that it's 47% and instead support the assumption that it's really less than 47%. That's why we got a value so low. So which of these answers is that conclusion? If the p is low, the null must go. If the test statistic is more extreme than the critical value and falls in the critical region, then you reject the null. So we want to reject the null. And does that mean there's not sufficient evidence to support the claim? No, it means there is sufficient evidence to support the claim that the real proportion is not 47%, but is actually less than 47%. So we draw that conclusion in order to complete the hypothesis test. I know this is a lot, and I'm going to tack this video on to what we were doing in the slideshows earlier, but this does put a cap on how the significance level gives us a way to assess whether the test of our hypothesis allows us to support the hypothesis claim because there's sufficient evidence to do so, or we fail to reject the null because there is not sufficient evidence to support the claim that we made.